Hello and welcome to this instructional video on the Perspective Short Circuit Current Calculator, which is among a suite of 10 tools that are designed to allow a competent electrical engineer to determine the severity of an arc flash incident. My name's Mike Frayne and I'm the creator of the European Arc Guide and also the author of the book The European Arc Flash Guide. To use some of the incident energy tools, it will be necessary to estimate the perspective short circuit current at the equipment to be worked upon. The calculator is based upon the impedance method, which will provide an RMS symmetrical short circuit current, which can be inputted directly into the incident energy calculator. There's also a separate output of maximum and minimum fault currents in accordance with IEC 60909 short circuit currents in three-phase AC systems. This will be required for the DGUV German calculator, and also a reciprocal of the XR/R ratio which is given. That will also be required by that calculator. To access the calculator, select the Calculators tab and then Perspective Short Circuit Current. If you select Expand or Collapse, you'll be able to provide preset configurations which will reduce the need for repeated data entry where the same conditions are being used in several calculations. The second option is to click on Instructions, and this will give you access to comprehensive guidance on how to use a calculator. You're strongly urged to acquaint yourselves with the instructions and also the limitations given. As can be seen from this single line diagram, the range of the calculator is to provide the fault current given a high voltage source, a transformer and up to 3 levels of low voltage distribution to SB3, which is the point of work. You can omit the transformer or any of the cables should you wish. Going back to the calculator, we can start to populate the data fields. From the transformer size, and as you can see, there's a range of up to 3 MVA. Let's pick the 1000 kVA option, or 1 MVA, with a primary voltage of 10 kV. Next, the primary short circuit current of 12 kA, and a secondary of 400 volts. Note that the primary and secondary voltage go up to 20 kV and 600 volts respectively. The transformer impedance, and we'll use 5.1%, can be entered here, and that figure is nearly always displayed on the nameplate. And finally, the supply source X/R ratio can be changed from the default value of 15, which is given here. If there is no transformer, you can choose Not Applicable in the transformer size field that is shown here. Now we can start to enter the cable details, and the first thing to do is to enter how many cables are required from the supply source. We'll enter 3. Cable 1 will usually be the transformer tails and be single core construction. Next is the conductor material, and we'll choose aluminium as there are 3 480mm cables in parallel. The cable installation method that we'll use is a delta layout, and this can be seen in the diagram here. The length of the cables is 8 meters, and we can enter this in the following field. Cable 2 is a 4-core cable with copper conductors, and there are 2 cables in parallel. The cable installation method is a 3-phase composite cable, and we'll put the length at 75 meters. Cable 3 is a 4-core cable with copper conductors but with no cables in parallel. The cable installation method is a 3-phase composite cable, and the length is 50 meters. If we press the submit button, you can see that we have values for the prospective short circuit current at the transformer LV terminals, and this is 25.88 kiloamps. Also at the equipment, which is 12.35 kiloamps. We also have an X/R ratio of 1.65, and the IEC 60909 maximum minimum prospective short circuit currents of 12.97 and 11.07 kiloamps respectively. This button, labelled Use PSCC in Incident Energy, will allow the voltage and the prospective short circuit current to be transferred to the incident energy calculator as shown. We can then change the parameters, and when we press the submit button again, the arcing current and the reduced arcing current is displayed, as you can see here. By referring to the upstream protection curve characteristic, a time to clear the fault current is entered, and we have the incident energy and arc flash boundary as shown again. There are separate instructions and an instructional video on the use of the incident energy calculator in the guide portal. I do hope that you enjoy using the calculator in the field, either on your phone or tablet or on your PC, and that you find this and the guide to be a valuable resource to discover and manage dangerous levels of electrical instant energy in the workplace. Thank you.